So our next speaker is Michael Bowlan. He's going to talk to us about evaluations conducted at the NOAA Hazardous Weather Test Bed. I believe that's the 2017 spring experiment. Michael has over 6 years working with meteorological topics, including research on thunderstorms from dual Doppler analysis of supercell thunderstorms and their structure to cloud electrification and lightning research. His primary responsibilities include working with the users of GOES-16 data, ensuring various products get into operations via his current position with the Storm Prediction Center. So welcome, Michael. Which one is it? Is it this one? NUCAPS. Okay, that's right. Use this mouse.
All right, thank you, Christy and everybody, for having me here today. So you heard a little bit about NUCAPS from Dan earlier, and Nadia is going to talk quite a bit more about NUCAPS after the lunch break. But I'm going to talk a little bit about NUCAPS and the demonstration, particularly at the Hazardous Weather Test Bed 2017 Satellite Proving Ground Experiment. So as Christy said, my current position is the GOES-16 liaison. I'm at the Storm Prediction Center in Norman. I've been there for a little bit now, so my primary focus is on GOES, but I'm working a lot on JPSS NUCAPS, as those soundings can be useful in Storm Prediction Center operations as well as WFO operations as well. So I'm going to talk a little bit about the demonstration, a little bit about the Hazardous Weather Test Bed, and give a little bit of some example cases and some feedback from the experiment this past year. Usually we have a spring experiment, and this year was a little bit later, and I'll talk about that later. So just a little bit about the HWT, for those of you that might not know exactly what it is and what we do there. So we're a part of the Experimental Warning Program. So the mission of this program is to improve the prediction of severe convective weather events at the quote-unquote warning scale, usually in that kind of 0 to 2 hour framework. It's located in Norman. The HWT is located right directly in between the Storm Prediction Center and the Norman Forecast Office, as a room right directly in between there. So they have large community of researchers, operational meteorologists, as well as students from the University of Oklahoma, and some industry that's also located all within that building or in that block of buildings around the National Weather Center there. We aim at the Experimental Warning Program to serve all National Weather Service WFOs and the CWSUs nationwide. And we're a vital component to research operations process, so a lot of experimental products are brought to the HWT and experimented there with forecasters that we bring in. They provide feedback. Those algorithms are then taken and improved so that they can be useful in operations down the road to the forecasters. So for the GOES-R JPSS experiment this last year, in 2017, we started a little bit later. We were usually in the spring, April to May timeframe. This year we were, or last year I guess, we were in June and July. So we ran for 4 weeks, beginning the 19th of June and running through the week July 17th, off 1 week for July 4th holiday there. We had 3 NWS forecasters, 1 broadcast meteorologist each week, for a total of 16 forecasters. And so what we do at the HWT, we use AWIPS2. Forecasters are there to evaluate the experimental products, and in this case, we're able to use the GOES-16 real-time imagery, and that's why we had a later experiment this year, so we make sure to have as many of the GOES-16 products available to the forecasters at this point. So the forecasters issue experimental mesoscale forecast updates when they come in for the first part of the day. Using these experimental products or operational products, this was the case this year, via a blog. Dan mentioned the HWT blog earlier in the case that he showed. And so we have a blog, the forecasters write to this blog. They'll issue a mesoscale forecast update, kind of what they expect to unfold throughout the next few hours of the day, and show some of these experimental products. And then they issue severe thunderstorm and tornado warnings as the convection unfolds throughout the day via AWIPS 2, experimental warnings as they would in their office, obviously not going out as real warnings, but issue the same as they would in their office. And so the goal of the experiment is we really want the forecasters to think about how they're using these experimental products in their nowcast and warning decision-making process, and how these products can help improve that process and be incorporated into their already busy process of issuing warnings. And we have numerous forms of feedback that we collect throughout the week. The forecasters take a daily survey each day, Monday through Thursday. There's an end-of-week survey on Friday morning. We also have debrief discussions every morning whenever we meet back, Tuesday through Friday before we start for the day. And then obviously have real-time interaction and discussions with the forecasters as the events are ongoing. And then one of the biggest forms of feedback the recent few years has been this blog. So this is where the forecasters issue pretty much everything that they use these products for. So they issue their forecast updates, reasoning behind their warning decision that they might have chosen to do, updates to previous warnings, forecasts, some of the best practices that they've found using these products, some ideas for improvement that they have for the products that they would like to see before they would want to use it in operations. And then any other thoughts and feedback that the forecasters would have, whether it be good or bad, about those products are issued via the blog. And there's a link there to the blog, the HWT Satellite Proving Ground blog. It can also easily be found just Googling that there if you want to take a look at some of the things that forecasters have written. And then we have a weekly webinar each Friday at noon where the forecasters present a case or two that they had from the week with using these products, and some feedback that they give then as well. So I'm going to talk about the NUCAPS, or the NOAA Unique Combined Atmospheric Processing System within the 2017 experiment. So the NUCAPS algorithm generates temperature and moisture profiles using information from instruments aboard JPSS. So for the experiment this year, we're using the profiles from SUMI NPP, the polar orbiting satellite, and also, as you see down there, kind of the second bullet, we also pulled in profiles from MEDOP-A and MEDOP-B, the European polar orbiters as well, which they overpass kind of the mid to late morning time frames over the CONUS. And the products that we included that we looked at were the NUCAPS profile availability, the quality control flags, which are the green, yellow, red dots you see there in that lower right image, the temperature and moisture profiles themselves from those three satellites, an experimental modified NUCAPS temperature and moisture profile. So this experimental NUCAPS actually pulls in kind of one of the drawbacks to NUCAPS is the boundary layer isn't resolved real well from the satellite, which is an important aspect to convective forecasting, obviously. And so this experimental modified NUCAPS pulls in a boundary layer modification scheme that's used. So that was the first year for that, so we evaluated that this year. And then also a multi-level gridded plan views of the thermodynamic, of NUCAPS thermodynamic information. So I'll show you kind of examples from all of these from this last year's experiment. So moving into some example cases and some feedback that forecasters provided. So this is actually the case that Dan talked briefly about in his presentation. I'm actually using the same case here. So this is one where he talked about the inversion, and this was used in a fire/convection case where the forecaster looked at here. So you see the NUCAPS sounding up here in the upper left, where Dan talked about. And you can see that inversion that's resolved in the 700, 850 millibar layer or so there. So the forecaster detected this noticeable inversion just near or above 700 millibars, and compared to the HER sounding, which I show here, as well as the RAP and NAM soundings, were also looked at in this case, taken at a similar time. That guidance was unable to really detect that feature there. And so The forecaster noticed a smoke plume on the radar from the Billings radar. This was in Montana at this time. So he's using the Billings radar, investigating a smoke plume down road, and we had convection that was kind of off to the west of this fire that he saw there. So the convection was going to be moving into this area. Saw this smoke plume, saw this inversion, wanted to investigate to see maybe how the convection moving into the area might react with that inversion being there, not being resolved in the models. So here's a 4-panel. We have this is using GOES data. Obviously, there's GOES visible data in the upper left, and this is the fire temperature RGB from GOES, where you see the fire there in the bright red near Bernie, Montana, and you see the kind of convection off to the west-northwest, moving into the area. Some light, moderate convection, nothing real major on this day, and then you have some radar images there as well showing the convection. So the placement of the fire and smoke plume the forecaster saw after his analysis suggests some of the accuracy of the NUCAPS capture of the inversion. So he was able to, he trusted the NUCAPS sounding there, the profile, because of that, because of its placement of the inversion and where he saw it on the radar. So he was able to see the smoke plume on the radar down here. He has an upper level tilt. Seems like that it went up to about 9,000 feet according to the radar, which is around where the NUCAPS profile had the inversion as well. So if you know smoke plumes, they'll go up. Once they hit an inversion, can spread out horizontally, which you're seeing here on the radar. So that allowed him to trust the NUCAPS profile in that case. And as this convection, which wasn't real strong in the first place, moved into the area, it was pretty much totally dissipated later on, a couple hours down the road after we get past here. So that can be a result of many things, but the inversion is obviously one of those that could play a role in the convection dissipating as it moves in. All right. Also, NUCAPS using during storm interrogation. So we, primarily NUCAPS. The soundings are used in a pre-convective environment for the most part, just looking at values of CAPE, other thermodynamic fields that forecasters are interested in forecasting for convective initiation, when and where it might occur. But this is an example of using NUCAPS during storm interrogation and having ongoing storms. So in this case, the forecaster used the NUCAPS sounding, quickly identified 0C and minus 20C levels from the observation of the NUCAPS sounding, instead of relying on models or a sounding from 6 hours previously in the early or late morning time frames. And so those levels are important for the forecaster monitoring their hail growth zones. How strong the CAPE is in those regions can correlate to hail size and distribution. So those are important levels for the forecasters that they want to see from these soundings. So they found the information very valuable during the warning operations. Use these heights when assessing the heights of the 50 and 60 dBz cores of storms that they were analyzing, which helped in warning issuance and relating that to hail size, which can be disseminated to the public for their safety as well in the warnings. So here's some of compare the operational versus some experimental sounding. Let's see. So this is a special sounding from Aberdeen. I think we're in Aberdeen, South Dakota for this case. So this is a special 18Z sounding that was launched from the Aberdeen Forecast Office. As you can see, much more, it's not as smooth as the NUCAPS soundings look. So you can tell this is an actual observation from a radio sonde from a balloon that they launched there. You can see a very well mixed layer, very high, has a kind of an upper level, mid-level inversion that's shown there. Going to the NUCAPS profile, this is just the operational NUCAPS. Now, it also shows a very well mixed layer. Has an inversion. It's quite a bit lower than what's shown in the observation here. Observation is around 500 millibars. This one's more around 700 or so. So quite a bit lower in the atmosphere. It did resolve an inversion, but didn't particularly have it in the right place, as opposed to the operational launch sounding. It's also quite a bit drier. We see in the boundary layer has quite a bit of dry bias in the NUCAPS soundings, not able to resolve that boundary layer moisture really well. Looking from the top down, it gets kind of washed out before it gets to the boundary layer there, which is very important when looking at convection. So looking at this experimental sounding, I'll kind of go back and forth here. So here's the operational NUCAPS, and then here's the experimental sounding as well. So what the experimental does is it uses observations from RTMA, temperature and dew point observations, and then through algorithm combines and creates this kind of boundary layer, well-mixed layer that it creates. But what it does is it does correct the surface dew point, goes up quite a bit from, I can't really see the numbers on here real well, but a good 10 or 15 degree increase in the surface dew point there, which acts to very much increase the CAPE and some of those other thermodynamic fields that forecasters are looking at in a sounding. One thing it does do is it just creates this well-mixed layer. Obviously, that's not seen in the real world a whole lot. It can be seen out west quite a bit, but in the plains or in the east, you don't really get those well-mixed boundary layers real often. So that's one thing that I think will be worked on in the coming years with these soundings, getting those boundary layers looking more like the real time. So this helped the forecasters. They like these soundings. They liked having both soundings. Really, they like having just the total observations as well as having this experimental sounding, because it corrects for that surface dew point, getting kind of more realistic values of CAPE, more that align with models and other observations that are seen as well. But there can still be plenty more work done here. And so all these experimental soundings do is modify the boundary layer, and they don't change anything else above where they show the boundary layer height. So looking some of the gridded NUCAPS, so this just takes the NUCAPS profiles in a swath and puts them on a gridded plan view where you can look at different thermodynamic fields that a forecaster might want to look at. So this is 850 to 700 millibar lapse rates compared to the RAP model on the right. The gridded NUCAPS is on the left. One thing you notice, obviously, is that the NUCAPS is a lot more coarse with the 40-kilometer resolution there. But overall here, you can see it lines up pretty well with what the RAP model is saying for these lapse rates. So this can just help to increase confidence in the forecaster that either the model's correct or the NUCAP's correct, these that go together here. And then you're missing some data where you have clouds. That's where the black spots are. So where there's clouds or where the retrievals are bad, you see no data there. But overall, the forecaster used these and thought that it provided good assessment of the mid-level conditions in this case. And then looking at this one is mixing ratio. So you can see 700 millibars on the top, 850 millibars on the bottom, with the NUCAPS on the left and the RAP model on the right that the forecaster was comparing to. So overall, here's where you can kind of see as we get a little lower in the atmosphere, the NUCAPS profiles become a little less reliable in some cases. So at the 700 millibars, it lines up pretty well with the RAP model. The mixing ratio here, as you get down to 850, starts to diverge a little bit from some of the RAP model guidance, as well as some of the other observations taken in the area. So overall, kind of as you got closer to the surface, the forecaster found here, it looked like there's a tendency of NUCAPS to trend towards a drier solution than what the models or observations are saying, as can be seen in the soundings as well. So just kind of a summary of some of the feedback that's collected this year. So they found the availability of the NUCAPS soundings beneficial in the field, particularly for the western U.S. and other data void regions where there's not really very many soundings. They love having the soundings, in that early afternoon time frame, as Dan attested to. Having those soundings in is really important for convective forecasting, instead of having to rely on soundings that were several hours old. So they really like having those 18Z to 20Z soundings in those time frames. Some work can be done to increase its utility, the field, better temporal resolution. The latency is obviously kind of the biggest thing for them. They doesn't really get in front of them for an hour and a half or 2 hours from the actual observation time. If they a lot of the forecasters told me, if they could see that reduced to, 30 minutes, under an hour at least, and that would have a lot more operational utility to them. Also, some of the gridded data, a little ragged at times, could be tailored for some better fields of interest. You kind of have to choose pressure levels and those things. They'd rather have just like surface-based CAPE, something like that they could just choose from a menu or something like that. Let's see, multiple passes during the day. So the more soundings that they can look at, the better, really. So if they have SNPP, NOAA 20, MEDOP A, B, having all those just lined up around each other, they really like having the more observations to them, the better, particularly in convective forecasting. Like having both the soundings and the gridded data. The gridded NUCAPS, like I said, they're found to be a little clunky at first. Kind of have to go through the volume browser and all this stuff in AWIPS 2. If you're not familiar with that, it's a little bit of a clunky mess to get through everything. It could be streamlined more into menus or something like that if it was going to be of operational use. I think other than that, that's all I have. So there's a picture of the test bed. Their forecast office is over here. The Storm Prediction Center is off over to the right. So, thank you.
Thank you, Michael. Thank you.